Namaste, everybody. I am Atreya Vedantam. I am a student. I'm pursuing Bachelor of Technology in Electrical Engineering at IIT Madras. And I think today I will explain the linear programming. It's NCERT 12th chapter, 12th class. Uh, so, what is linear programming? A brief introduction. Well, from the heading itself, we can conclude there's something to do with lines, right? And you would not be wrong. Many other things that we deal in today's world are best dealt with lines because first thing is the humans can interpret the meaning of lines pretty well and pretty easily. So, for example, as opposed to a parabola, which is harder to predict, it's difficult to say whether this is a parabola or whether this is an exponential, right? But this is easy to say that it's a line. So that's something that humans are good at. So programming. Well, that the second part is a little slightly more complicated. It's not as obvious as what it seems to be. Programming essentially it is the manipulation of lines to get to optimize. So right now, I think this is something that's really important in today's world. Like the entire uh, the world is behind optimization algorithms, and it's become very relevant in today's world. So such class of problems which seek to minimize or maximize profit. So that's what we're trying to do in this chapter. They're called optimization problems. Okay, you want to optimize, you just maximize. So in any situation, your optimization is very important. Like if you want to enjoy your breakfast, you need to optimize you need to optimize your health versus your taste. If you really like some food, eating too much of food can be bad for the health, but it might give you joy because if you've eaten some tasty food. You have to optimize how much time you need to spend, studying versus playing sports or spending time with friends. These are various kind of optimization problems that we face in day-to-day life. So it's very important knowing how to solve them. So this is a special class of optimization problems. Okay, it's called linear programming. So here, basically, this is an introduction to what it is basically saying. Basically, you are given a few constraints, right? And this is something that happens in every day, right? You're given a few constraints, like maybe you can't travel to another country by tomorrow, right? That's a constraint that many people might have. And you need to maximize or minimize, basically optimize a certain function. That's called the objective function. And here in this chapter is represented by Z. Okay. Now this function can be a function of some variables. It can be a function of two variables. I know that in 12th standard, you only you guys only do calculus with one variable. But basically, this is small introduction into a function can depend on multiple parameters, right? So it can be a function of multiple variables. You can take inputs from multiple different points and output a single number. So that is called objective function. You need to maximize this function. So why is linear, by the way? Why not ax squared? Well, that's why we are doing linear programming. So that's why it's not a generalized optimization process. We are only dealing with certain linear programming problems. Okay. So here, the function is linear in x and y, and we're trying to maximize it given a few constraints. So, for example, this is the example given. I think it's just easy to read through. It's how a dealer can maximize his profit, but with the constraints that he has, like his storage space, like his investment money, the money he has, capital. So these are called constraints. They're written like this. So these are investment constraints, these are storage constraints, and you're trying to maximize some objective function like this. So there are a couple of points here to know. X and Y are called decision variables. They're called decision variables. They are used, basically they drive the decision process, right? Then you have constraints, which with this detail above. Then these are something called optimization algorithms, problems basically. Optimization algorithms are techniques used to solve optimization problems. So graphical, you can solve linear programming problems through different ways. Okay, so here we'll be focusing on the graphical method. So you're given, so you state all this work, all the constraints. Okay, and then you ask, can I maximize a certain uh, objective function? Okay, so that is what that's the question you're trying to ask. Okay, so okay, so now there are a couple of terminologies. The region in which you have a feasible solution, that is the region in the XY plane which satisfies all the constraints that you have, all the four constraints that you have here, is called a feasible region. And here you can see that this is the region. How do you arrive at that? Well, this is some basic mathematical plotting. If you wanted to plot the region x greater than 0 in XY plane, that would basically mean all the values in which x is greater than 0. So that would be that region. If you wanted to plot y is greater than 0, it would be the region where y is greater than 0, which is here. So if you wanted a common region, if you wanted to find both the conditions, then you would have to take intersection of both the sets. That is only this region is common to both, right? So that is the basis of how optimization, how you would write various constraints into the XY plane. Now you may ask, okay, why XY plane? What if we have like three variables? What if the objective is dependent on x, y, maybe z? Then yeah, surely this will be a three-dimensional linear programming problem, and it will be significantly more difficult, which we don't have to tackle in 12th grade. So feasible solutions are points on inside or on this region which can solve the four constraints. Basically, any point inside the region or on the region satisfy all four constraints and therefore are a viable value that you can consider. You can consider taking. Like, for example, maybe in an abstract sense, maybe going to school tomorrow is a feasible option. It lies inside the region. Whereas going to, I'm not sure, some other country, let's say, maybe outside the region. So you can clearly see that such a point can never even it's not never even allowed. So it isn't. You don't need to waste your time considering. There is just something that is allowed. So maybe it might optimize. Nobody's saying that this is the optimal solution, but maybe it might optimize the objective function that you want to maximize or minimize. So again, you have something called feasible solutions. Feasible solutions which are not feasible, they lie outside the feasible region. And you have optimal solutions. So now you see that there are infinitely many points within a given region, right? So how would you try to find out the optimal point? Optimal point meaning the point of x comma y such that z is maximum. So that is the definition of. Okay, so the way you do that is, so this is a theorem. Okay, if R is a feasible region, right? Some region like that. If that is a region, then the theorem says that the feasible point, the optimal points can only occur on the vertices or on the sharp edge. Okay, so that's what this is. Again, this theorem also says that if R is bounded, that means what is the definition of bound? That there exists, this is suitable for there exists a circle with R greater than 0 such that R belongs to a circle of radius R. That is the definition of a bound. Any bounded thing can be enclosed by a circle of a certain radius, a real radius. Okay, if R is unbounded, then there need not be an optimal point for you to control. So here's a simple example of how they found out the optimal points for the given region. I think the example above had something like that, right? So you only needed to check 4 points, and the maximum happened to be the point of the maximum. And this happens to be the minimum. I mean, nobody obviously wants to minimize their profits, but I mean, assuming that this did not correspond to profits, you might want to minimize, right? Let's say you want to minimize loss, right? Maybe this might be the minimum loss. Okay. So now there's got a corner point method. I think fairly obvious because that's what we are doing. So that's it. This basically details the process of what we're going to do, but that's something that we'll just explain. So that shouldn't be too much of an issue. So we'll just go ahead with we just look through a few examples. Okay, let's solve the examples. Solve. So again, you find a feasible region. That's the region. You just examine all the corner points. Whatever gives you the maximum is the optimum. It's the same case here also. You look at all the points. whatever is the minimum. If you're asked for a minimum, you're asked to minimize, right? Read the question carefully. So that would mean this is the okay. Now you know that there are multiple optimal solutions in this case because both these points correspond to the optimization. In fact, it's actually pretty easy to detect when multiple optimal solutions occur. Okay, so when do they occur? When you want to optimize an objective function that looks like that, this is basically 3 into x plus 3, right? And you know that a constraint itself is like this, which means that a constraint, the constraint is parallel to such a like objective function, which means which means all the points x comma y such that x plus 3y is equal to 16 are allowed by these four constraints, right? I mean, not all points, but there is some point, right? Some x, y, such that this is allowed. Then this automatically is 3 into 16 because you don't need to know what x and y are specifically, right? So all of the infinite points such that x plus y, 3y, 60 within the feasible region will give you a 180. And if that happens to maximum, then any of the points will give you the optimal solution. So then again here it's a example of how you cannot find the smallest region. Actually, there's a slightly cleverer way of doing this, which I'll explain in a moment. So you want to minimize, we want to minimize this, right? So what you do is you plot this graph. Okay, assume z is some real number. Okay, why would you do that? Well, you want to try to minimize this value, right? So when you're trying to minimize, you try to look at all the possible values of z that it can take, and what is the maximum z, right? So let us take some z that we can just guess z, okay? Here. So for example, this is z that they have guessed. They've not guessed it actually, but let us guess, okay? So we guess actually, since it's minus 30, our z is actually minus 300, right? So this line corresponds to z of 300. Now, does this lie within the feasible region? So that's a question you need to ask. If yes, that means z is 300 is definitely possible, right? Now, you try to increase that slightly. If you increase that, note that that the line shifts like this, right? Which means as you increase that, yeah, all of these lines are possible. All of this is possible, right? Because they all lie within the region. Until at some point here, you have to reach a certain maximum here. You see, that maximum is what you obtain from 100. You see, this is a much better way of doing it. Now, what if you decrease that? Well, it becomes like that and that and that and that and that. But you know that any line like this will always have a feasible region because this point, this line extends to infinity. So you'll have some any line here will pass through the feasible region, which means minimum is actually minus infinity. That there is no corresponding point to act. There's no real point to actually minimize the function. Well, this is actually a bad statement, right? It means what I mean to say is that minimum tends to minimum. There's really no x value that can start. Again, this is another example. So we'll just get started with the problems. Okay. So first, we graph everything. We only need the first quadrant because x and y are both correct answer. X plus y less than square. So we just need to. So the graph looks like that. You want to maximize 3x plus 4y, right? So again, as per the method that I suggest, first let's guess some value of 3x plus 4. Okay, let's say 3x plus 4y is equal to 4. Okay, let's just guess that. Okay, let's not guess that. You know, it may make it slightly obvious. If you guess this line, how do you plot this? Well, you know that when x is 1, 3x equals 3. So this will be something like that. And when x is 0, y is 3 by 4. 3 by 4 is something like that. So the slope is like that, right? So which means as you increase this, let's say you make it 4 now, okay? So now y is let's plot something. This 3 by 4 is 1, right? Now if you make it 4, this becomes 1 and this becomes 4 by 3. So you see the line is moving this way. So as you increase it more and more and more, you know that at a point you're going to touch. You're going to touch that, right? You're going to touch this point, 4, 0. You're going to touch 4, 0. As you increase it more and more and more, all of these, you know, clearly there are feasible points which are more. So all of these points lie on these lines have a z value which is greater than whatever value that was for this line, right? Which means this cannot be maximum. You understand the logic? Basically, so if you keep increasing this z value, the line shifts upwards like this, right? But for all of these lines, you know that they pass through the feasible region, which means all of these are feasible points. And since for all of these feasible points, the z value is more than this z value, this clearly cannot be the point of optimality, right? Until you increase it like that, and that, until you reach this point, which is the maximum point. So from this, you can easily conclude that 0,4 is the maximum point, and therefore the maximum pressure value is right on this. The maximum of z is equal to 16. 3 into 0 plus 4 into 4. That is the answer. Okay. Minimize something. Minimize this one. So okay. Here we again have the first quadrant. X plus 2y less than 8. So x is 8. Y is 4. So the line looks like that. Okay, that's a constraint. Again, less than. So note that when I say less than, it's clearly is like this. Okay, I just don't want to denote it all the time because it's very messy. Okay, I just draw the lines which bound the thing, and I think it's obvious to see looking at the inequality sign, it's obvious to deduce which region the graph is on, right? Less than always corresponds to either down or to the left, and greater than or equal to always corresponds to up or to the right. Okay, and then we have 3x plus 2y less than 12, which is over here. So you note that I'm denoting the second constraint with a blue line for clarity. This will be 6. That is the second line. Okay, sorry, it's a bad line. So which means the critical points are that, and right. So that's it. So again, what is this point? This is 0, 0. This is 4, 0. This is 0, 4. This is some point which is correspond to the intersection of x plus 2y is equal to 8 and 3x plus 2y is equal to 1. We just subtract this. Minus 2x is equal to minus 4. X is equal to 2. So 2 comma x plus 2y should be 8, right? 3, right? Basically, it's solving for intersection, solving the two line equations. Should not be very hard. It is basically just subtracting the equation, eliminating y, and then solving for x. Then you can substitute it back in the value of x to calculate the value of y. So add these 4 points. So clearly the optimal point must lie in some of these 4, any of these 4 points. So we just calculate z at all of the points. So here z will simply be minus 3x, right? Minus 6 plus 4 into y. 4 into 3 is 12. Here z will be minus 12. Z will be 0. Z will be 16. Clearly this is the minimum. So minimum of z is minus 12. And you should also write the point, okay? That's important. You always write at 4, 0. Here also at 0, 4. So as you can see, I've done problem 1 and problem 2 in 2 different methods. It's for more diversity. Problem 1, I've done it using my own method. I mean, it's not my own method. It's a different method that is given from the textbook rather than the textbook. And then second one, I just started using the textbook method. As you can see that there's not much difference. The method that I've done in problem 1, it gives you slightly better clarity on what exactly is happening, right? If you move the line up, then you know that this value of z, which is objective function, is increasing. That gives you a little bit of insight. Third question. Again, right now, from now on, it's just, you're doing the same problem over and over again. Once you get a hang of it, it's just practice. I just solve other anyway. Right? So third question is solved here. Here are your axes. 3x plus 5y less than 15. 5 and 3. So this is the way I draw these lines. Okay, it's a simple way. You know that any 2 points can describe a line active entirely, right? So I substitute y is 0, I get x is 5. So that's what I put here. Substitute x is 0, I get y 0, 3. Then I just join those two. Similarly, 2. So that is the feasible region. So these are the corner points. 0, 0, 2, 0, 0, 3. And what is this point? Well, again, we need to solve for the intersection. Solving for the intersection, I think. So we can multiply the first one by 2. 6x plus 10y is equal to 30. And this one by 5. 25x plus 10y is equal to 50. Subtracting, you get 19x, 20. So you get 20 by 19, comma. You get 20 by 19, comma, 91, right? 95s are 450. 450 plus 60 is 510. 510 by 19. 510 by 19 is sadly 30. Let's see if I have made a mistake. I think it's 45. Yeah, this is 45. So at 45, 50, so I think it's easy to at this point. It is the road calculation. Z clearly here is 0. Z clearly here is 10. Z clearly here is 9. See, note that I'm just putting x and y into this Z. You see, I'm not doing anything complicated. Just 5 into whatever x is plus 3 into whatever y is. So that's 9. And then putting plugging Z in, here you just get 235 by 90. So clearly the maximum is, well, let's see, 1989 is approximately 180, so this should be the maximum. So, okay, I just erase all the time. So the maximum value is, so at 20 by 19, 45 by 19. Weird answer, but I think it definitely seems like a correct answer. Max of Z equals 235 by 19. Okay, then we have the fourth one. Minimize again. I think at this point, okay, 2, 2, right? That's how you draw this thing. X plus 3y is 3, 3, 1. You draw current these two, and you connect these two, and you try to solve for what is this point, and this point, and this point. Wait, my bad. I think I made a silly mistake. So yeah, one must be careful. I mean, I just thought I could get away with it, but you clearly see that indicating the reason is important. So look at the sign carefully. It's greater than 3. This is greater than 2, which means that the feasible region is like that for x plus y is greater than 2, and the feasible region for x plus 3 greater than 3 lies like. So which means the common feasible region lies in that region. Okay, so that is the feasible region. If you want to minimize 3x plus 5y, you can try it using the method that I did in the first one. Take 3x plus 5y to be some random. Let's say it's 3, okay? Which means you have 3x, if 3x plus 5y is 3, you have x is 1, and y is some 5 by 3, right? You have this kind of 5 by 3 is 2. Wait, so 5 by 3 is 2.6. It's a bad idea. So let's say y is y is 2. Okay, so let's say y is 2 by 5. Okay, then and let's say y is 2 by 5 and x is 0. Okay, so then y is around here. Actually, no. I think you can let y be 5. Okay, if y is 5, y is 5. So if then let's plot for this 3x plus 5y equals 5. Okay, so then this happens to be that, and then 3, this is 5 by 3, right? X becomes 5 by 3. So this is the line, right? Now as you slowly increase it upwards, you know that the line is going to get like that. It's going to move towards that, right? Let me use a slightly different. So you know the line is going to move like that, right? So that's your objective function. As you move your z up and up and up, remember that for this value it's infeasible because none of the line never passes through any of the feasible region, right? But you keep increasing until you see when it becomes feasible, right? And then the moment it becomes feasible, that happens to be the minimum value. So you keep doing that until you see that actually this is the minimum point, right? It's pretty obvious to see. But then what is the minimum point? We need to solve for these two equations again. That is the pain part. But here we are, x plus 3y is equal to 3, x plus y is equal to 2. can subtract them off to give you 2y is equal to 1, y is equal to half, or x is equal to 3 by 2. So therefore, we have, therefore we have at 3 by 2 comma half, minimum of z is 3 into 3 by 2, 9 by 2 plus 5 by 2, 14 by 2, which is 7. Again, we erase this for the next problem. Okay. Now, 5. Again, we're doing the same thing. X plus 2y is less than 10, so that should be 10. That should be the thing. 3x plus 5y is less than 15. So that should be 5, and 15 should be somewhere there. And therefore, the corner points of this region are that, right? So now we just need to maximize. You need to maximize. By now I think you've got enough practice to see exactly what kind of points we maximize, right? You can see that at 0, 5 it's 10, at 5, 0 it's 15, at 0, 0 it's 0, and at this point it should be something else, right? So let's check what the intersection point is. 3x plus y is 15 and x plus 2y is 10, right? So if you just subtract, 2x minus y is 5, right? Then if you add first and second, third equation, you get 5x is equal to 20. In other words, x is 4. In other words, y is 3. Okay. So yes, 4, 3 here, right? Now 4, 3, what is the value of z? Z is equal to 3 into 4, which is 12, plus 2 into 3, which is 6, 18. 18 is the maximum, therefore, that's the answer. So again, at 4, 3, max of z is equal to 80. So that's done. See, by now I think there's a sort of rhythm that you might have developed. Basically, doing this problem for so long, there might be some intuition that you can take back from this. Like, okay, like we don't need to actually just blindly substitute numbers, and the intuition that you can actually take away is you look at the coefficients of this x and y. Okay, now, okay, so the system will try this kind of intuitive approach. Okay, so in this intuitive approach, you need to minimize x plus 2y. So now try to think of what kind of a line x plus 2y would be. Since the coefficient of x is like half the coefficient of y, right? Numerically, when you have something like ax plus by, you can imagine that this line is going to be much very quite flat, right? At the same time, something like 100x plus y is going to look very steep. And so now you can see kind of the trade-off, right? In any sort of constraint which you have here, let's try to detail the constraint. Okay, here, unfortunately, I think the constraints are fine. So 2x plus y is greater than or equal to 3, which means, that the curve is going to look steep like that. X plus 2y is greater than or equal to 6. So, the curve is going to look kind of flat. Okay, how flat? Well, look at this. Both of them intersect at y is equal to 3. Okay, that's a nice point, right? And then if both are greater than 0, so y is equal to 3 is a common intersection. So the common feasible region is that, right? Anything above. So what this actually tells us is that since you're trying to minimize this kind of a very flat curve, right? Now we have to look at the relative flatness. Is x plus 2y flatter than x plus 2y is equal to 6? No, because there's the same amount of flatness. There's the same slope actually. So it's kind of simple to solve, right? You don't need to look at any other corner points, any of that. Just by some intuition, you can see since these slopes are both the same, you know that z is equal to x plus 2y line is going to be something like that. It's going to have the same slope as that, right? So as you just pull this upwards, your z is going to increase at a point where these two lines will simply merge. And at all of these points where it is feasible to have a solution, that will be the minimum possible z, right? So one of those points is 0, 3, so you can just evaluate it there. So writing solution may at, and actually you can't say at what, because at all of these points on this line, the minimum value is obtained. So you can say at x plus 2y is equal to, at x plus 2y is equal to 6. Okay, that's the line. At this line, the minimum of Z is achieved and it's okay. So okay, now for 7, 8, 9, and 10, we need to show that the minimum minimize and maximize something subject to a public specification. So now we are given three constraints. So let's solve that. X plus y is greater than 60. So again, that should be 60, that should be 60, right? And greater than means the region is x minus 2y is greater than 0. What does that mean? So let us write that carefully. X greater than or equal to y, right? These two mean the same thing. What is x is 2y? Let's draw that line. It's going to be a flat line, kind of like that. And x is greater than 2y means the, oops, my bad. The region is going to be something like that. That plus that, right? Now x plus 2y is less than 120. So you know that 2y 120, so it meets at y is equal to 60 and x at 120. So it's going to be like less than. So which means your feasible region is that. Okay, that is your feasible region. So basically inside this. Oh wait, x is greater than 2y. My bad. So you see that your feasible region is this silly issue. If x is greater than or equal to y is less than or equal to x by 2. Which means when you plot y is equal to 2, you look at all the points which have a y value less than that line. So it should be below. So I think it's a good practice whenever you're plotting inequalities to always write the y on the left side and then the less than, greater than, and then some functions. Then you can decide above or below by just looking at the inequality side. Okay. So anyway, you have that. So all the corner points are available to you here, and here. So I think it's just a matter of calculation. No, this 60, 0, this 120, 0. These 2 points are x is equal to 2y meeting with x plus y is 60. So you can substitute that. 2y plus y is 60. So y is equal to 20. So this is 40, 20. Okay, and then the other one is again x equal to y meeting x plus 2y is 120, right? So but this time x is equal to 2y. So 4y is equal to 120. So y is equal to 30. So x is equal to 60. So 60, 30. We need to minimize and maximize. So find what is z. Z at 60, 30 is simply 5 into 60, 300 plus 300, 600. Z at 40, 20 is 200 plus 200, 400, right? At 120, 0, also it is 600, right? Oh, okay. Oh, my bad. I think I misunderstood. So when this is shown the minimum occurs at more than 2 points, they mean for question 6. And I think that's what we've shown, right? We have shown that the minimum occurs at that center line. Okay. Now, again, here also, if you think about it, the slope of this, which is 5 into x plus 2y, is the same slope as the constraint. And whenever that happens, you know that there are going to be infinite optimal points. So all of the points on this line, x plus 2y is 120, are actually optimal points, and they all yields 60, 0 will simply give you 300. Right? So you know that the minimum is there for that, maximum is there for that. So I'll write answers. Minimize 300, maximum 600 at 60, 0. And this one is at all points of x plus 2y is equal to 120. Okay, now in the 8th one, we need to minimize and maximize. Again, once again, you can see that x plus 2y has the same slope as one of the constraint. This means that there are going to be infinite critical optimal points, and they're all going to lie on that. So again, you can just notice this by looking at the objective and all constraints. So looking at the constraints, this time y is greater than or equal to 2x. Okay, so if you plot that, that is the region. So then you have 2x plus y less than 200. So you plot that as 100 here. 2x plus y is less than 200. So that is the line. X plus 2y is greater than 100. Oh, so that should be 50. So that should be something like that. So this time the region is something, which means the optimal points are going to be here, 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 and here. Well, here this is 0, 50. This is 0, 200. And these 2 points something we need to calculate. So first, this point is the intersection of the line of y is equal to 2x and x plus 2y is equal to 100. So if you plug that in, you will get 5x equal to 100, x is 20, and this one is simply going to be 25 comma 50. No, 50 comma 100. That's a guess actually. But you can easily verify one, right? You need something that's twice, and that sum should be 200. So that's that. And now it's a pretty simple calculation again. So z at each of these values. What is z at 0, 200? That is 400. Z at 0, 50 is 100. Z at 20, 40 is 20 plus 80, which is 100. Again, this is something that we already predicted. Remember, I just said that because the slope of the objective function is the same as the constraint, it act as if you're drawing the line like this, like that, and then increasing z slowly. And at the minimum possible, at the minimum z where you can get a optimal point, you try to find its value. But since that coincides with the line, all points here are optimal points. So at all points you get 100 as a minimum. Then you have 550, 100. Well, actually, just by graph, look at this. So as you go on increasing this line, it goes like that, like that, like that. It's pretty obvious to see that this is a maximum. This is the last point which is allowed, right? Beyond which there's no other feasible point in that line. So you know that the max actually is achieved at 0, 200. So there's really no point in calculating this. So once again, I'll write down the answer. 400 is the maximum. Okay, I'll write minimum maximum. Minimum is 100, 400 is maximum. Minimum occurs at x plus 2y is equal to 100 all points, or not all points, by the way. Whenever I say this, it doesn't mean all the points. It means all the points which lie in the feasible region. Clearly, the entire line is not feasible. 400 is simply achieved at 0, 200. Okay, now we'll do the ninth problem. Nothing else in the heart of linear programming. 9 is simply going to be x is greater than 3. So you draw x is equal to 3, and everything greater than is the part of the thing. Y is equal to 0 is here, x-axis. So that is simply, that is also that. I mean, that is actually the entire thing. We're interested in the common reason. X plus y is greater than 5. So we have 5 here. So anything, oh, sorry, my bad. Anything like that is feasible for that region. So currently the common feasible region is that. Now x plus 2y greater than 6. So y is equal to 3. So clearly this means 3, 2, right? That's very, very easy to see. So y is equal to 3 should, I mean, sadly this is drawn, my bad. Y is equal to 3 if it's there, x is equal to 6 somewhere there. Before we draw an incorrect diagram, I think it's useful to first solve and ensure. Okay, so we'll be doing that. X equal to 3 will probably be here, and this will be 3. That will be y is equal to. That will be x equal to 6. And then if you want to find intersection point is y is equal to 1, and x is equal to 4. Right? Your 1 is intersection point here. So it's not to worry. It's possible. So this means since this is x equal to 3, the feasible region is now. So that's a critical point. It's a critical point. And on. Okay. Now we are trying to maximize, right? Well, maximize. We are trying to maximize minus x plus 2y. Remember, okay? Very important. Now, because of the negative slope, it's actually possible to maximize. Let's see how. Okay. Let's first. Okay. One thing to do is we can just the method given by textbook is really hard. I mean, we can write down the critical points and we can analyze as we can analyze what happens if you extend beyond the critical points, right? That's the way I can prove that there is no minimum. But this intuitive graphical method is actually quite easy. So we'll do that. If you want to plot z is equal to minus x plus 2y, you clearly see that it has a positive slope, right? With a slope of like half, right? So if z is equal to 0 actually, this slope has a slope of half, which is something like, right? So now as you move Z up and down, if you increase it, right? If you actually increase it, then the graph moves upwards like that. That's because y is equal to x by 2 plus z by 2, right? So as z increases, then this line also increases. So one thing we immediately notice is that no matter how much we move upwards, this region is always going to contain some line, right? This any of these lines is going to contain a feasible point, because as you move z upwards, this line is going to pass through some amount of the feasible region, which means that there is no maximum, no finite maximum. See, that is very easy to show, right? Otherwise, it would have been really hard to find out all the critical points. Critical point, what I mean by critical points is optimal points. Okay, and find out all that, but now it's rather easy. Okay, now 10th one. Maximize verifiable expression y subject to these three conditions, these four conditions. First, xy greater than 0, so you focus your attention on the first quadrant. Y is less than or equal to x. So draw y is equal to x and say that the y less than x lies there. Okay, y less than x plus 1. So what is y less than x plus 1? Will happens to be a line like that. Okay, y is also less than x plus 1. But we didn't know that because we didn't need to know that actually. That's because we already knew that this is true, right? And as long as it's true, this is always true. So okay, so the feasible region is that. That is the feasible region. We need to maximize x plus y. X plus y clearly, x plus y is, so, okay. Okay. Oh, sorry. I think I made a mistake. Y is greater than or equal to x minus x plus 1. So, which means that the feasible region for this constraint is here. The feasible region for this constraint lies here. Since there's no feasible region, there is no max. No possible max value. Actually, forget max value. There's no possible value at all. Okay, so that's it. I think we are done with exercise. So again, just to revise, these are called decision variables x and y. You can even have multiple variables, but here we are only dealing with two because we want to draw things on a play class. Non-negative, right? You want this to be real, applicable real life, but there was no issue really. I mean, you can possibly even have negative values in certain circumstances. These are linear constraints. They're not quadratic constraints. Why is if this was a constraint, then you would have to look into all of that. Okay, but that is not. This is small historical notes.